Hello and welcome to Mathematics Illuminated, where I shed light on any and all math topics from simple to advanced in a way that's easy to understand and interesting to learn. Please subscribe to my channel as I continue to post more videos, and comment below on videos you'd like to see in the future. Today I am going to go over how to prove that the integral from a to b of 1 over x dx is equal to the natural log of b minus the natural log of a. I will attempt a careful evaluation at this problem, showing the method of how it is proven. The idea behind this video comes from a comment on my video about Euler's number, where I go over this formula without proving it. I am asked to see this proof, which is what this video is for. I'll leave a link to my video on Euler's number in the description, though in that video I assume my viewers aren't familiar with calculus, where in this video I will assume you at least have a basic understanding of calculus concepts, as I will be using calculus to prove this. So, let's begin. First, I'll go over what is significant about this integral. Remember that 1 over x can be written as x to the negative 1. There is a formula that exists for finding the integral of x to a certain power, and it's that the indefinite integral of x to the a dx is equal to x to the a plus 1 over a plus 1. Now let's see what happens when I plug negative 1 in for a. First, we notice that the denominator becomes 0, and we are left with 1 over 0, which is undefined. So, clearly this formula is not helpful. That's why this proof is so significant, because it requires steps outside this formula. So, how will I solve this? This proof has 6 steps. First, I'll go over the fundamental theorem of calculus, then I'll go over the chain rule and how it applies to our problem, then I'll go over proving the derivative of e to the x, which will help in the next step where I prove the derivative of e to the f of x using the chain rule, then I will prove the derivative of the natural log of x using the previous steps, then I'll finish off the proof by using the fundamental theorem of calculus to tie this all together, getting us the desired result. So, let's start. This is the fundamental theorem of calculus. I will be using this as part of the basis for my proof. It states that the integral from a to b of the derivative of a function f of x is equal to f of b minus f of a. If I use natural log of x as my f of x, and the derivative of f of x as 1 over x, which is yet to be proved, I can substitute these into the fundamental theorem of calculus to get our desired result. So, all that is left now is to prove that the derivative of f of x when f of x is the natural log of x is 1 over x, or proving that the derivative of the natural log of x is 1 over x. And to begin doing this, I'm going to go into the next step of my proof. Now I'll go over the chain rule. One thing to keep in mind, if you're unfamiliar with calculus, is that the derivative of f of x can also be written as d over dx of f of x. What we're trying to prove using the chain rule is that the derivative of e to the f of x is equal to e to the f of x multiplied by the derivative of f of x. The chain rule states that the derivative of g of f of x, where g of x and f of x are both functions, is equal to g derivative f of x multiplied by the derivative of f of x. This is a common rule in calculus. Here we are going to use e to the x as our g of x, which means that g of f of x is going to be e to the f of x. Here I'm going to mention that audibly, this may all be very hard to understand. If you're confused, try replaying this section or try to pay extra attention to the symbols on the screen. Feel free to leave a comment if you'd like help understanding anything. Substituting our g of f of x into the chain rule gives us this. Now what we must do is solve for the derivative of g of x, which is the derivative of e to the x. Because once we have solved for that, we can plug the derivative of g of x into what we have here. So step 3 is going to be trying to solve for the derivative of e to the x. What we're going to do is we're going to use the limit definition of the derivative, which is how derivatives are defined in calculus. The limit definition is that the derivative of g of x is the limit as the change of x approaches 0 of g of x plus the change of x minus g of x all over the change of x. Knowing that g of x is equal to e to the x, we can rewrite the derivative using the limit definition. Using exponential rules, we can rewrite e to the x plus the change of x as e to the x multiplied by e to the change of x. Now we can factor out the e to the x. Now we can put the e to the x outside the limit, since the limit only involves the change of x, which isn't present in the expression e to the x. What we need to do now is evaluate this limit, and I'll begin at evaluating it by substituting y in for the change of x. So now we're trying to find the limit as y approaches 0 of e to the y minus 1 all over y. Here I have the graph of e to the y minus 1 over y. We can see that as y approaches 0, x, or the limit, approaches 1. So we know that our limit is equal to 1. There is a way to prove this more mathematically than just looking at the graph, but I won't go over that in this video. Let me know in the comments if that's something you'd like to see in the future. So now that we know this limit, we can substitute it in for here, and multiplying by 1 just gives us e to the x. So now we know that the derivative of e to the x is e to the x. This is something else that I mentioned in my video about Euler's number, so there's a proof for it. So going back to what we have here, we know that the derivative of e to the x is just e to the x. Now we can move on to the fourth part of our proof, which is proving the derivative of e to the f of x, which we already started doing earlier with the chain rule. Now that we have our derivative of g to the x, we can substitute it in here, which gets us e to the f of x. And recall that's what we were trying to prove. So now that we have proved this, we can continue in our proof. Let's put this to the side to reference in a bit. Let's move on to the fifth step of the proof, which is proving the derivative of the natural log of x, which is what we were trying to do a lot earlier in this proof. First, I'll begin by writing the same thing on both sides of an equal sign, the derivative of e to the natural log of x. On the right side, we'll acknowledge that e to the natural log of x is equal to x by the definition of the natural log. And we know that the derivative of x is just 1, which is just calculus at its very basics. Notice that we can call f of x equal to the natural log of x, and we can use the formula in the top right. Using the formula, we can see that we are left with e to the natural log of x multiplied by the derivative of f of x, where recall f of x is the natural log. And of course, we know that e to the natural log x is just x. Now divide both sides by x to solve for the derivative of f of x. This allows us to prove that the derivative of natural log of x is 1 over x, since recall f of x is the natural log of x. So now that we have proved this, we can come back to the last part of our proof, where we come back to the fundamental theorem of calculus. Recall at the very start of this proof, we showed how we need to prove that the derivative of the natural log of x is just 1 over x, which we have just done. Now we can substitute these into the fundamental theorem of calculus, and at last we have our desired result. This proof was very complicated in some parts, but we got there. If there's anything you'd like me to clarify about this proof, leave a comment. Thanks for watching! Please subscribe if you found this interesting. Farewell for now.